Good morning. All right, so let's look at these announcements and we're going to get into some new material here. Your next assignment is due on Sunday at the beginning of class. I've already mentioned that last problem requires a little bit of an explanation, so please let me know if you've got any questions on the assignment. I got a couple of emails for the last one, students asking questions, and for the most part it's usually the simple things. You need just a little nudge on interpreting the problem statement, or maybe there's a certain thing that's confusing you, and I'm more than happy to do my best to answer that. So, come by my office hours, give me a call, send me an email, anything I can do to help you out. I'm more than happy to do that. Okay, so a week from today, you've got your first quiz of the semester, and that's nothing to be nervous about. The quizzes aren't worth too many points. What you should do to prepare for that quiz is just understand the homework assignments that you've submitted. Because it's one thing to put a solution onto the paper, and it's another thing to really understand how it all happened. And the quizzes are designed to pick out the students who really knew how to solve the problem and understand the concepts. So we'll have our first one on Tuesday. Today we're going to be talking about vapor pressure and hydrostatics. So do you have any questions before we get into that new stuff? It includes just Chapter 2. Yeah, the first two homework assignments, the one that you submitted on Sunday and then this one that you're submitting next week. Yeah. Other questions? All right. This is one of the problems that you are assigned to do, and I'd like to explain some of the key ideas of this problem, just to get you started in the right way. This is problem 237. And so let's visualize what's happening in this problem. You have a hollow pipe and a solid cylinder that's falling downward through that hollow pipe. And there's this small gap between the two because the solid cylinder has a diameter of 100 millimeters and the hollow pipe has a diameter of 100.5 millimeters. So what's the size of this gap? Careful, yeah, it's 0.25 millimeters because the gap distance is on either side. The problem statement says to assume it's falling through the middle of that gap. And so really, if you think in 3 dimensions, there's a ring all the way around it. And they're saying that the ring spacing is the same everywhere. So what you need to know partly is that gap distance. You also need to know that this is lubricated with oil. They've got a small, thin layer of oil between there. And they tell you the temperature and the type of oil. But just to eliminate any uncertainty here, I'm just going to tell you to use this viscosity. You can verify it in the back of the book. But just so we're all on the same page, we're going to use 0.35 Newton seconds per meter squared as the viscosity for that. So this is a shear force problem, and we also know that the weight of this cylinder is 15 newtons. And so that force is acting downward. And this is an equilibrium problem. They're asking, when all of the forces are in balance, what speed is it falling downward? So what does equilibrium mean? We've talked about equilibrium already, briefly, but it means what? Equilibrium means the forces are equal. Everything's in balance. It's not accelerating. It's not slowing down. In equilibrium, it means that the forces are in balance. And so I already told you that the weight is acting down, and this whole thing is moving down. And so if the weight is acting down, what other force is there that it's in equilibrium with? Yeah? There's a force going up, right. So what is causing, this cylinder has something that's pushing up on it. What's pushing up on the cylinder? Something about the surface, right? Because think about, there's oil all around the edge of that surface. Do you remember the problem we did with the plate, and it was in a tank of glycerin, and we were pulling on the plate? This problem is similar to that problem. And so what you need to consider, I'm not going to tell you everything for this, but I want to give you some of the key ideas. You need to consider the forces that are acting on that solid cylinder, the direction of the forces, and one of them is going to be the shear force. Weight is down, shear force is up in this. And so here's the equation for shear force. We've seen this before. We used this same equation on that plate problem. And on the plate problem, what we had was the viscosity of the fluid. We had some gap distance dy. We had a velocity that it was moving, the force, and the area. On this problem, the area was, like the top area and the bottom area. It was whatever area is touching the oil. And so the same thing you're going to have to consider for this cylinder. You're going to have to wonder, what area should I use for this cylinder? What is that critical contact? Where is the friction that is being lubricated against? Why did they put that oil in there? You have to consider the gap distance, because the gap distance is what goes into this dy. And so those are some of the key ideas of that. I think that's all I want to say. I don't want to say too much because I want to leave some of the struggle for you. Remember, we talked about how you get stronger through the struggle. So that's me spotting you. Standing above you, you wouldn't want me to spot you in the gym. You'd get choked, right? All right, but that's a little bit of help for that problem. Here's another one that's similar to what we were talking about last time in class. Remember, we took a look at a picture of a bug. And I wanted to emphasize that in the case of one of these bug problems, I mentioned it in class, but here it is again. When we have the surface tension equation, this is what it looks like if we take a cross-sectional look at the bug's leg. It's deflecting the water in two places. And so the length that we have to use here in the equation for the surface tension, it's the physical length of the bug's leg, but it's on either side of the bug's leg that it's pressing down on the water. So you need to double the physical length of the bug's leg in order to find the force that can be supported by whatever that liquid is. So just that hint and reminder for this problem 59. Any questions about either of these problems before we get into the new material? The falling cylinder or the bug? I like questions, so don't feel like you're doing a bad thing if you ask a question. All right. Those are two of my favorite questions from the whole semester in the homework set, especially that cylinder one. I've been asking that cylinder question for years and years, and I still love it. It's just like a beautiful problem for me. Let me dim the lights so we can take a good look at this one. All right, so what's happening in this picture? Boiling water. What does the word boiling mean? Okay, we're giving it heat. That's a component of it. You can see at the bottom there, this is a very hot flame. It's blue. We can tell sort of the temperature by the color. That's one of the indicators that it's boiling. What if we dissect this image like some sort of an image analyst? How else do we know that it's boiling versus not just heating up? Okay, you can sort of see some bubbles. Right, and you said water bubbles. I'm glad you said that, because sometimes we think, well, it must be air. Those are air bubbles. But those aren't air bubbles. Those are actually bubbles of H2O vapor. We just think, well, air is around us, so the air got into the water when it was heated up. But no, that is H2O that was a liquid turning into a gas, and then it's escaping out of the top, because the gas has a low density, it floats to the surface, and then it enters the atmosphere. And then we have some more indications, if we just analyze this image, that there's a gas being formed. If you look above the surface of the water, you can see that there's steam on the glass, and then these little bubbles of condensation at the top. You can see little water droplets, because some of that steam is cooling off and collecting and condensing. And so there are some very definite visual cues here that this is boiling water. All right, so we looked at boiling water for 2 minutes. Why? It's because we're going to be talking about that process of, the other one. We're going to be talking about the process of how liquids go into a vapor state, and different ways of doing that besides adding heat. Adding heat isn't the only way to get water to enter the vapor phase. So at sea level, Water boils at 100 degrees Celsius. At Mount Everest, water would boil at 69 degrees Celsius. Why do you suppose that is? Is it because Mount Everest is haunted and lots of people have died up there and it's like a magical thing? Pressure difference? Yeah, all right. So more details. Like, why would a difference in pressure, do you think, account for this, this temperature differential? Any ideas? Okay. Well, let's go through some of this material. Some of these definitions may help to answer it. Vapor pressure is a word that we're going to refer to a lot through the semester, and it'll come up again when you get into water resources. It's the pressure at which a liquid will boil. And vapor pressure increases when temperature increases. Let me do a little sketch on the board here of a basin of water that we're adding heat to. All right, so here's a basin of water, and oh boy, these drawings are just the worst. So here's our heat source. That's my flames. All right. When water is boiling, it has a tendency to get out of the liquid state and enter the vapor state. And what we're saying is that when it's boiling, how anxious, I'm going to try attributing like human properties to the water. Of course, the water isn't anxious. It doesn't feel anything. But if you'll indulge me, I'm going to describe it this way. The water is trying to get out into the gas phase. Here's the air pressure pushing down on the liquid. And then here's the pressure of the vapor pressure of the liquid. So at boiling, the vapor pressure, as we call it, sort of like its escape intensity, is exactly equal to the pressure of the air. So that when the water was cool, it didn't have very much vapor pressure. And that's why it evaporates slowly when water is cool, is because the molecules themselves don't have as much kinetic energy. So they're bouncing around, but they're not bouncing very hard at that top surface trying to escape. Not very many of the water molecules have enough kinetic energy to volatilize. Some of them do because, you know, they're bouncing around. The water molecules are bouncing around, and then maybe 3 or 4 in a row will bounce into one of the molecules, and so it has a lot of speed and has enough speed to go up into the air. It has enough kinetic energy to vaporize. But not very many of the particles, if we talk about the probability of it, not many of them have enough kinetic energy to go up into the atmosphere. But what we know is that as we heat it up, the vapor pressure increases, and so more of those molecules will have enough kinetic energy to escape. Here is some tabular data that shows the vapor pressure of water as a function of temperature. And we know that the standard pressure of Earth's atmosphere, 1 atmosphere, is equal to 760 millimeters of mercury. You might remember that from like a physics class or a chemistry class. But that is like 1 atmosphere is equal to 760 millimeters of mercury. So at 100 Celsius, that is when water has as much vapor pressure as the atmospheric pressure. So if we go back to Mount Everest, there's not very much atmosphere up there, so the water doesn't have to have as much kinetic energy to begin boiling. So there's less of this up on top here. There's less air pressure, and so we don't have to heat up the water as much before it starts to vaporize. And an interesting side effect of this thing is that sometimes on recipes, on the back of the box, like if it's for a cake, it will have what they call high altitude instructions. Like they actually say in the recipe, if you're baking a cake, maybe you should use less water, because they know that if you live at a high altitude, the water is going to evaporate out of the cake more easily. No, wait, I guess they're saying add more water. Yeah, because the water is going to evaporate out of the recipe more easily, and so they have to change the proportions of things a little bit. So that whole high altitude instructions are because of vapor pressure and the temperature effects. So here's another way of looking at this tabular data. If we have a graph of it, you can see it's not a linear relationship. It's not a very, like even trend. It's the vapor pressure is slowly increasing, and then it rockets upward very quickly as you approach boiling. one of the things I do back in the United States, I live on some land out in the woods, and I have a lot of maple trees at my house. And so in the wintertime, we drill holes into the maple trees, and the trees have water coming out of it, and you boil it down to a syrup. Maybe you've had pancakes before, like it's a very sweet syrup. You could put it on kanafa. It tastes pretty good that way. But if you're boiling the water at 80, it evaporates kind of slow. You have to take these gallons and gallons of water, and you have to build a very high, heavy, intense fire so that you get the vapor pressure as high as possible so you can boil it away very quickly. So 100 degrees is when at standard atmospheric pressure the water will start to boil. But you can make water boil at other temperatures. In fact, you can make water boil at room temperature. Here in this room, I could make this water boil without adding any heat. Any ideas how you could do that? You have to deal with the pressure. Remember, this is two things. You can either increase the temperature to increase the vapor pressure, or you can adjust the atmospheric pressure above it. And that's what we're going to look at on a video that I've got in just a minute. Here is vapor pressure. You can look it up in the back of your book, and you need to for one of your homework problems. I think it's that last one when I say you need to explain something. That problem has to do with vapor pressure. So it tells you some temperature of a water, so you need to go to a table, a vapor pressure table, and compare the vapor pressure that it's describing to whatever it's asking about. Okay. Let me see if this is going to work. I just turned on my internet.
We're going to demonstrate reduced pressure boiling by creating a vacuum in a glass vacuum jar and using an Edwards pump. By using and applying vacuum, we're making water change from liquid to vapor very quickly and very effectively. Water at room temperature is placed into a beaker before putting it into a glass vacuum dome. We now open the vacuum isolation valve. You can soon see the vacuum gauge showing around 20 millibars of pressure. This is significant because it's the vapor pressure of water, and therefore the point at which it will boil at room temperature. At atmospheric pressure, water boils when heated to 100 degrees Celsius. That's because it's the point when water vapor pressure is equal to atmospheric pressure, and water begins to change phase from liquid to vapor. In this demonstration, we don't add any heat, but instead reduce the pressure. When this pressure is equal to the water vapor pressure, the water boils or changes phase, but at a much lower temperature. In fact, the energy for boiling is coming from the water, and consequently its temperature reduces. And as the pressure becomes lower, the water will eventually freeze. You'll see that even when removed from the vacuum chamber, the water remains frozen. A simple process, but one that's widely used in the pharmaceuticals and food packaging industries.
All right, when I watched that the first time, I was a little confused about why it froze. I wasn't expecting that part of it. So let's talk about the two different things that happened in that video. The first one we were kind of expecting because we've already been talking about it. We've already been talking about how that when you reduce the pressure above it, then it's going to start to boil. But the thing about it also changing the temperature is because, remember, anytime you have you ever used that compressed air before, like to blow off a computer screen, or a spray bottle of hairspray, and a lot of it came out? Anything goes when there's a change of phase. I don't know why it's not changing. When there's a change of phase, it requires a temperature to do that. All right, there we go. So when you're going from liquid to gas, it requires energy for those molecules to go into the gas phase, and so it was taking the energy from the water, and that's why it froze. Not only was it changing phase, but it was using some of the heat that was built into the water. But the main thing that I wanted to show you is that down here on this table, this is the vapor pressure of water. And so if you take the atmosphere surrounding some water down to below this value, then it's going to boil. So in that bell was a vacuum relative to gauge pressure. So here's the water, and surrounding it is a sealed container, and they're pumping out the air. And once the pressure inside that bell, let's say it was room temperature, so the temperature of the water is 20 degrees Celsius, and so the P sub V, which is what we use for vapor pressure, the P sub V is 2340. 2340 pascals. So as soon as they took that below 2340 pascals, then it started to boil. So if we took this to 2000 pascals, then there's a little bit of pressure holding the water down, but more pressure for it trying to escape, and it begins to boil. So that's our first glance at vapor pressure, and we'll come back to it again in Chapter 5. Any questions so far? Part of the reason it's important is because of a process called cavitation. And what cavitation is, when there are pumps, you have to be very careful that the pressure inside of the pump doesn't go below the vapor pressure of water, because the water might begin to boil inside of the pump. And if the water starts to boil inside of the pump, the tiny little vapor bubbles, they'll collapse once they get onto the other side of the pump. Once they get upstream of the blades, then those little vapor bubbles instantly collapse, and it sends a small shock wave through the water. And one of those little shock waves doesn't do too much damage. It maybe just causes a small chip in the impeller blade. But over time, those little chips in the impeller blade wear away at it and cause erosion. And so this is a look at some generators at a hydroelectric facility in Russia. It was a really big, beautiful dam that produced a lot of electricity in central Russia. But because there was some cavitation forming inside of those generators, the whole facility was destroyed because there was a catastrophic failure of one of their generators. It got off balance, and in a sense, it exploded, and the whole facility was destroyed. And so that's sort of one of the reasons cavitation is something that we have to be careful about, is it can cause a lot of damage to equipment. And cavitation is just the word we use to describe vapor pressure of the water. It starts to boil inside an enclosed environment. Okay, so that's it for vapor pressure for now. The rest of the class we're going to be talking about pressure intensity. And usually we don't use the full word pressure intensity. We just say pressure. It means the same thing. And we've already looked at the units of pascals before. Pascal is the same thing as a Newton, which is a unit of force, spread out over a square meter of area. And it works in all directions. Pressure doesn't only come from above. Pressure comes in all directions. So if you go down into the sea at a deep elevation, it's not like you can turn your head and avoid the pressure on your ears. And if you've ever been scuba diving before or snorkeling, you know that once you get below 2 meters or so, it really starts to hurt your ears, and you have to sort of blow on your nose and get the pressure to equilibrate. But it's coming in all directions, so it doesn't matter the orientation. It only matters the depth to measure the pressure. So here's a little trick question. If we have two different reservoirs, you can think of it as like a lake. One of the lakes is very wide, and one of the lakes is very narrow. At the bottom of the lake, we're interested in the pressure. So which one of these lakes has a greater pressure? The lake on the right, which is large, or the lake on the left, which is small? This is one of those trick questions. You got to be careful about those ones, right? It's hard to see, but these have the same depth. Both of these lakes are the same depth, and so it doesn't matter. At the bottom, the pressures are equal, because the pressure only depends on how much liquid is above you. not how much liquid is on either side of you. It only matters the amount of liquid above that's causing the pressure. And so sometimes they'll test like submarines in very small lakes that they couldn't drive around in, but it's deep enough so that they can simulate the pressure that they need to evaluate. And so one of these trick questions here, they both have the same pressure at the bottom. So let's look at the law that governs that. This is called the hydrostatic equation. And so much that we do in fluid mechanics is derived from the hydrostatic equation. What it says is that the change in pressure with respect to elevation is equal to negative gamma. Who remembers what gamma represents? What is that symbol? Specific weight? Sometimes we call it the specific gravity. What's the number we use for gamma? 9810 when we're talking about water. And the units of gamma are what? Newtons per cubic meter. It's a measure of how much weight there is per unit volume. And so here is our 1 cubic meter. So 1 cubic meter of water is 9810 newtons. That's the amount of weight that a cubic meter has. So this equation is saying as you go down through the fluid, so as d sub z is getting lower, the pressure is going to be increasing. I mean, we kind of already know that from our physical experience in the world, that when you go down, the pressure gets higher. So here's our z datum. We're measuring elevation above this point. And so any height that we have above the z datum is a positive z. So let's say if we're starting here, then z is getting lower. And what this formula says is that the change in pressure, dP, is dz times negative gamma. So that negative sign, I want to make sure that we understand the interpretation of that. If we're going down, dz is negative as well. So going down through the fluid, dz is negative, and so we have a negative multiplied by a negative, and so it's a positive, and so dP is going higher as dz is going lower. That's why that negative sign is there, is because they're opposite directions. Conversely, you can think of it this way. If you're here and your elevation is getting bigger, and what's happening to your pressure? It's getting lower, right? You're going upward through the fluid, so the pressure is being relieved. So the pressure is going lower as you increase the elevation. Now gamma, the significance of that particular amount, let's look at the units here for dz times negative gamma. Gamma we already know is newtons per meter cubed. What are the units of dz? Meters, right? So meters multiplied by newtons per meter cubed gives us newtons per meter squared, right? And that's the same as a Pascal, which is what we're looking for pressure. We know that we measure pressure with pascals, or we can even just call it newtons per meter squared, and that's fine. So that's the hydrostatic equation. And looking at the units, this should make sense for us, that everything works out. What it means is you go down through the fluid, every meter of depth through water increases the pressure by 9810 pascals. So if you swim 1 meter under a swimming pool, the pressure there is going to be 9.8 kilopascals. If you go 2 meters, then it would be 2 times 9.8 kilopascals. It would be 19.6 kilopascals. All right. All right. So this slide is titled Pressure Variation in Uniform Density. And I want to emphasize that last part, uniform density, because in this little illustration, it's a tank of just one kind of water. Later on, we're going to look at what if there was 2 different things in the tank. Later on, we'll look at what if there was oil and water in the tank. And we'd have to change our technique just a little bit. But so far, we're just considering as we go down through a fluid that isn't changing. It's the same liquid the whole way. And so let's assume that the density of the liquid and therefore the specific weight of the liquid are uniform inside of that fluid. And so we can integrate the hydrostatic equation, and we'll get something we'll call piezometric pressure. And what piezometric pressure, P sub z, is you're keeping track of the elevation, and so it's the pressure plus gamma times z. And z is just some distance above the elevation datum. And we can rearrange the piezometric pressure if we divide pressure by gamma and we divide gamma z by gamma, then we get something called piezometric head instead of piezometric pressure. And the difference between the two, if you look at the units of this first one, if you look at the units of piezometric pressure, it's going to have pascals as the units. But if you have this, both of these terms, the p divided by gamma and the z, those both have units of elevation, just meters. And so it's a different way of representing the same thing. And the hydrostatic equation says that inside of a tank, these two terms are going to be the same as we move through the fluid. So here in the tank, we can have location 1, we can have location 2, but the sum of the pressure head and the elevation head at 1 is equal to the sum of the pressure head and the elevation head at 2. There's no losses as we go between the two. And we'll take a look at that in some problem solving. Okay, here's the case that we're talking about. I've written the hydrostatic equation here, and we know at location 1 the elevation is 34 meters and our gauge pressure is 66,000 newtons per meter squared. What do I mean by gauge pressure? Right, pressure relative to atmospheric. So we're considering atmospheric pressure as being our 0 point. And so we know the elevation at location 2, and these elevations, maybe it's above sea level, maybe it's above the bottom of the tank, but it doesn't matter. Both of these elevations, both of these two have been measured relative to the same location, and that's all we need to know. What I'd like you to do is work with your colleagues there. I'm going to bring up the lights and stop talking for a minute, and I'd like you to use the hydrostatic equation, find the pressure at location 2 in terms of the gauge pressure. So that's what you're given initially. And then I'd also like you to find the absolute pressure at location 2. And you may need to flip through your notes to remind yourself how to convert between absolute and gauge pressure. But if you don't remember, eventually I'll pull up the solution and we'll take a look at it. But I'd like you to take a crack at this. Find the pressure at 2 using the hydrostatic equation. Okay, I try to practice my own suggestions, and I keep hammering home these two same suggestions. One is always write the units when you do the calculations, and the other is it's a great idea if you do a little sketch. So even though I was looking at the sketch when I solved this problem, I made my own just because it helps me to see and feel the problem. Okay, so we're given the hydrostatic equation. We know 2 elevations and 1 pressure. We want to find pressure 2. It's just a matter of substitutions. And if we think about the units, each one of these terms has units of meters. That's why we can add them together, is because newtons per meter squared divided by newtons per meter cubed, when I divide that, it's meters, plus meters, minus meters, so it's all meters, multiplied by newtons per meter cubed, so that will give me newtons per meter squared, which is the same as pascals. So you can see that I've converted it just for sake of expression to 144 kPa. And that's not necessary. It's still a correct answer if you say 144, 480 newtons per meter squared, or 144, 480 pascals. All three of those would be correct answers. So any questions so far about this one? You should be asking me, why do I have a triangle on the top of my water? And why these lines underneath the triangle? Any guess why I drew that? It means something specific, actually. It's like it has a symbolic interpretation. In fluid mechanics and hydraulic engineering, you'll sometimes see in drawings like this a little triangle at the water surface. And what that means is that it's open to the atmosphere. It means that this tank isn't closed off and pressurized. It means it's vented to the atmosphere. And these little ripples here, those little lines beneath the surface, it's supposed to simulate like the ripples or waves that you'd see on a water surface. And so that's another way of telling the viewer that this tank is open to the air. And so this isn't a pressurized headspace above the tank. All right. So then part two, how do we find the absolute pressure? Now we just add atmospheric to it. So let me scroll down. If we know the gauge pressure and the atmospheric, the solution here is the absolute is gauge plus atmosphere. If you think back to that drawing that we had that was relating the two, if you're measuring the pressure from the lower line, that lower line represents absolute zero pressure. So we want to find out how much pressure is there starting from vacuum as the basis of measurement, and it would be 245.8 kPa. Okay. So everybody feel pretty comfortable with the hydrostatic equation? Good. All right. It's an important one. Even though we spent the first part of class looking at videos and pictures of water boiling, the hydrostatic equation, that's a big idea. You're definitely getting your money's worth today. We can have the full equation written this way, or we can make it even a little bit simpler. It's already simple, but let's simplify it just a little step further and keep track of the change in pressure. Because often all we're interested in is how much did the pressure increase by us going down into a fluid a certain depth. And that's what this abbreviated hydrostatic equation says. It says your pressure change is a function of the elevation change multiplied by gamma, which is the unit weight of whatever the fluid is. By the way, if this problem is in oil, don't use the unit weight of water. The gamma that we're talking about is the gamma for whatever the fluid in question is, including this hydrostatic equation works for air and other gases. It doesn't only work for liquids. If we're wondering why is the pressure low at the top of Mount Everest, hydrostatic equation could be used to estimate the pressure change at the top of a mountain, because air has a unit weight gamma and there's a delta H because we're at the top of a mountain. So the change in pressure is a function of change of depth through some fluid. So let's try this abbreviated hydrostatic equation for Challenger Deep, which is that lowest part of the Mariana Trench at the bottom of the ocean. That is 10,911 meters under seawater, and seawater has a slightly more dense gamma than freshwater because it has salt dissolved into it. And so the unit weight of seawater is 10,100 newtons per meter cubed. So using the abbreviated hydrostatic equation, see if you can calculate the change in pressure from the surface of the ocean down to the bottom. You've got the delta H and you've got the gamma. All right, so here's the solution up on the screen. We're given the delta H from the surface to the bottom of the ocean. And the abbreviated hydrostatic equation, all we have to do is multiply the unit weight and the depth. and we get it's 110 MPa. And this is a gauge pressure, because what we were doing in this problem is we're saying, well, that's the change in pressure. If we said that atmosphere is 0, then the gauge pressure is 110.2 MPa, but absolute pressure, we have to add 101 kilopascals, which is the same as 0.1 megapascals. So the difference between 0.2 and 0.3, that little extra pressure is if we add on the effects of atmospheric, in the same way that we did in the previous problem. So any questions about that? All right. I noticed that a handful of you, a couple, have printed out the notes, but I don't think most students have yet. The notes are available online, and since we've got just a moment, let me show you where you can find those. It's on iLearn in a variety of different formats for you to choose from, whether you prefer 2 slides or 3 slides and so on. Oh, that's right, my internet's not on. Well, anyways, the notes are online. I won't bother showing you. You've seen our class page before because that's where you submitted your first assignment. On the left side, if you go to class notes, then you can see so many different varieties of how to print those out if you'd like to have them handy. Let's just take one look at the announcements before we finish for today. They are that you've got a homework assignment coming up. You now have everything you need to solve those problems. And then a week from today is quiz 1. So that's it for today. I will see you next week.